Hello everybody, my name is John Harper, member of technical staff at onsemi, and today I'd like to talk to you about understanding single pulse avalanche rating in SiC MOSFETs. On Semiconductor has a number of application notes on unclamped inductive switching, which is a method used to determine avalanche rating. Here is the application note AN7514, which covers single pulse unclamped inductive switching. So we have the unclamped inductive switching test circuit. Here is the gate driver, and the gate driver is driven with a certain pulse width. Then we have the gate resistance, we have the device under test, we have an inductor and a bus voltage here, VDD. And note there is no anti-parallel diode for the inductor. That means that when the device is switched off and current is flowing through an inductor, there is no limitation to the voltage, and this device will go into avalanche. So we see here in the waveforms, the device is driven for a time Tp. The current rises during that time and reaches a certain avalanche current rating, IAS, and then the device is switched off, goes into avalanche. So this represents the avalanche voltage. The current reduces rapidly, and then the sequence is completed. If the current is too high, the device will fail. So what we do is we increase Tp and do the tests repeatedly, letting the device cool down in between, of course, and then we increase the current until the device ultimately fails. And this is the reason for the IAS, which means single avalanche test. There is a repetitive avalanche test, which is not discussed in this presentation, but it's clear that you do repeated tests with allowing for the heating of the device. Let's have a look at the avalanche rating specification from our new 22 milliohm 1200 volt M3S SiC MOSFET. We specify in the datasheet the single pulse drain to source avalanche energy, EAS, at 267 millijoules, and this is measured with a inductance of 1 millihenry, and the current which causes the we guarantee works is 23 amps. Clearly the current which causes failure is much higher than that. We have to put a safety margin in there in our data sheets. So is this EAS of 267 millijoules always the same, or does it change? Let's have a look further. We take the data we just saw and put it in the formulas in application note 7514. We can calculate the EAS, which comes out more or less the same as what we just saw, and the TAV, the time in avalanche. This time in avalanche is a critical parameter. What we find is that the avalanche current time squared, so avalanche current times avalanche current, times the TAV, so I squared TAV is like I squared T for a fuse, is generally constant in the simplified models which you have. It's actually a little bit different with measured data, but this is a good initial model. So what we see is we can change the avalanche energy depending on what inductor value we choose. So this EAS is 59 millijoules, which looks very poor. That's if we use a very low inductor. If we want to make our part look good, we can use a large inductor value. 100 millihenries, for example, will give 1.2 millijoules. Makes it look good. However, we have to be realistic and say we have to measure the avalanche current and the avalanche time and actually plot that based on real measurements. We can't just calculate them. So key message here from at least the formula here is that EAS depends on the on the actual inductor value chosen. So by using a large inductor, you can make it look very good. The right way ultimately of specifying avalanche rating is with an avalanche rating plot of time in avalanche versus avalanche current. This is what we do on our data sheets. We've done this for many years on our automotive MOSFET data sheets, silicon MOSFET data sheets, and we do this on our SiC MOSFET data sheets. So as we see here, this represents the curves shown from the calculations in the previous slide, but it's actually based on measured data. The slope is slightly different. What we also see is the avalanche rating when you start at 25 degrees C is better than when you start from 150 degrees C. This is because the time it takes to reach the destruction temperature when you start at a high 150 degrees temperature is a shorter time in avalanche than with a 25 degrees C starting point. That's the reason for this difference. So this is actually based on measured data. Just want to point out all of our discrete SiC MOSFETs are 100% avalanche rated and 100% tested. So what are the conclusions? Conclusion number one is that avalanche energy data without a specified inductor value doesn't make sense. We can manipulate the avalanche energy data in our datasheet both by picking a large inductor value or using a small inductor value. The next point is how you really solve that problem above. Use a data plot of avalanche current versus time in avalanche. That shows the true avalanche or unclamped inductive stress performance of our devices. This has been used for a number of years in automotive silicon MOSFETs. We base this on measured data. I've been showing you how we derive that using calculated data, but for sure we base this on measured data by measuring points with a number of different avalanche currents. Thank you for listening.